Hey folks, and welcome to today's lecture. So if you remember from last time, at the very end of the lecture we finally introduced both the time-dependent and time-independent forms of the Schrödinger equation. And where we didn't really get to last time was talking about the so what of this equation. How do we interact with this equation in practice, and what makes it so useful? And so that is going to be our goal for both this lecture and the following two lectures. So by the end of the day, I'm hoping that we'll be able to use the time-independent Schrödinger equation in order to derive the wave function for an example potential v of x. And the example potential that we're going to pick is going to be called the infinite square well potential, or you'll see this referred to in the literature a couple different ways depending on if you're reading a chemistry or a physics textbook. And so don't be too surprised if you also see this referred to as either the particle on a line potential or sometimes the 1D particle in a box. And I want to note before getting started that I've derived most of this lecture based off of Griffith's Introduction to Quantum Mechanics. The third edition, section 2.2 is what is particularly useful. And so if you want some related reading, you can go ahead and check out that resource, or Atkins' Physical Chemistry textbook also does a fairly nice job on the subject. So what is this particle on a line? We're going to introduce what may seem at first to be a fairly dry potential. We're going to consider an arbitrary particle, and its potential is going to be defined by the piecewise function v of x is equal to 0 if x is between 0 and some constant L. Otherwise, the potential is going to be equal to infinity. So before we get started with this, it's always a good idea when you encounter a new function to have the very first thing that you do to be to plot the function. So let's go ahead and plot what this particle on a line potential looks like. So on my y-axis, I'm going to plot v of x, and on my x-axis, I'm going to plot the position x of the particle. And it appears that there's kind of two different points for x that are important to us, the points x equals 0 and the point x equals L. And so between 0 and L, the potential is equal to 0. And so we can go ahead and draw that this is a constant potential where the constant is equal to 0 between 0 and L. Otherwise, as soon as we get to x equals 0, this potential is going to shoot up to infinity. And similarly, after we go past L, this potential is also going to shoot up to infinity. And so this right here is our potential that we're talking about. What does this correspond to in physical reality? Well, let me make a couple comments on that. First off, a particle with this potential is something that can move around freely between 0 and L, but is prevented from traveling outside of these bounds by an infinite force. Remember that the force is the derivative of the potential energy. And so if v of x is equal to infinity, the force is also going to be equal to infinity. So a couple different examples of this where you would see it in real life is, for example, a marble that's rolling around on a frictionless horizontal track with perfectly elastic bumpers would be an example. Or, although I'm limited in my materials that I have available to me in my apartment, and I'm also unable to provide you with a completely frictionless surface, I have taken a little box here and put a tape dispenser in it, real DIY. And so what this particle might look like in real life is something that has the freedom to roll around within a certain space. But if you imagine the walls of this box being much, much taller, such that no matter how much energy, kinetic energy I put into the system, it couldn't escape this, I'm bounded for this particle to stay inside of this box. And what I want you to notice is that for today's lecture, we're purely talking about a one-dimensional case. So my particle is allowed to move left and right, but it is not allowed to move up and down, so this motion is forbidden, and it's not allowed to move backwards and forwards. So we're restricted to one-dimensional motion for this particle. And And our goal today is going to be to use the Schrodinger equation to solve for the wave function that describes or characterizes this particle that's subject to our particular square well potential. And so where we can start off with is thinking a little bit about the mathematics of this potential to start off. One thing that we are going to immediately notice is that because the potential is piecewise, so too is going to be the wave function. And so how I'm going to start representing this wave function is to say that the wave function is equal to some function, I don't know what it is yet, inside of the box, or inside of our little 1D line, and some other function outside of the box. And we're going to solve for both f of x and g of x in this lecture. And we'll start with g of x because it turns out to be solved not using math necessarily, but actually using our chemical intuition. And so here's the insight that we need to be able to come up with a functional form for g of x. We know that the potential is infinite outside of the box, right? So our particle, because these walls are infinitely tall, is not allowed to live out here, and it's not allowed to live out here. Another way of saying that is that the probability of that particle existing outside of the box is 0. And what we know from the Born interpretation of what the wave function represents is that if the probability of seeing the particle outside of the box is 0, then also that means that the wave function squared is equal to 0 in that area. And the only way that the wave function squared can equal to 0 is also if the wave function itself outside of the boundaries of the box is equal to 0. And so this makes our wave function a little bit easier to solve right off the bat. We know that g of x is equal to 0, or that the wave function has to be 0 outside of the boundaries of our box. So the more interesting part of the problem is, what is the wave function going to look like inside of the box, where the particle actually lives? And so in order to figure out that wave function, the time-independent Schrodinger equation is going to be our mechanism for solving for the wave function. Now, from last lecture, we learned that the general form of the time-independent Schrodinger equation is E, the energy of the system, times psi, the wave function, is equal to a couple of constants, negative h bar squared divided by 2m, m being the mass of the particle, times the second derivative of the wave function, plus a term that is the potential v of x times psi of x. And so maybe you can start to see why we're picking this particle in a box as our first example, because what is the potential inside of the box? Well, it's just 0. And so this second term is going to entirely cancel out. And our simplified version of the Schrodinger equation for our particle on a line is going to be that we want to solve for a potential or a wave function such that E times the wave function is equal to my constants times the second derivative of the wave function. Now, if you've taken a course in differential equations, this probably looks pretty familiar to you. It's called a second-order differential equation, and if you've taken that class, you may already know the answer to this question. If you haven't taken differential equations, which is most of us in this course, don't worry. I'm going to walk us through how it is that we can solve this equation, which looks a little bit different than something that you've seen before. And the answer to how we're going to solve for this is a tried and true technique called guess and check. So taking a step back and looking at this equation, I want you to notice that what we're searching for is, aside from a couple of multiplicative constants, which we'll worry about in a second, we're looking for some function where the function and its second derivative are the same thing. And I can only think of two functions that obey that property, sines and cosines. Now, you may be thinking something kind of sneaky like, wait a minute, what about e to the x and e to the negative x? Those two functions also work. There is a theorem in mathematics called Euler's theorem, which says that a sum of e to the x and e to the negative x is equal to a sum of sines and cosines. So they're really interrelated functions, and for today, I'm going to pick sines and cosines as our two functions that are distinct functions that both have the property that the function is equal to its own second derivative. And so I'm going to start off by essentially guessing a functional form for our wave function. I don't know exactly what it looks like or what the constants look like, but I do know that my function could have some sine character to it, and it could have some cosine character to it. And so just to hedge my bets, I'm going to say, well, there could be, if it's sine k of x, that would still have the property that it's equal to its own second derivative. Again, we're not worrying yet about the multiplicative constants. And also, it's okay if there's some prefactors in front. And so the most general form that I can give of what the wave function could look like is to express it as a sine of kx plus b cosine of k prime x, where a, b, k, and k prime are all constants, but potentially they could be different constants. I don't really know yet. My goal now is to, one, make sure that this actually, when I plug it into the Schrodinger equation, gives me that it obeys this governing equation. But two, I want to see if I can use information that I'm given in this problem and in this sample potential in order to figure out, is there anything more clever or more specific that I can say about these constants? And as a heads up, yes, there is, and we're going to talk about that. So to solve for our unknown constants, we need to start thinking about some of the constraints, or the boundary conditions is the technical mathematical term for it, that have to be true of our wave function. And so going back to lecture 2, if you remember, our wave function has to be continuous. And so because we said that our wave function is equal to 0, kind of at this point x equals L, and at the point x equals 0, that means that f of x also has to be equal to 0 at those 2 points. And so we're going to say that two of our boundary conditions are that psi of x equals 0 is equal to 0, because the wave function has to be continuous. And smooth. And same thing for psi of L is equal to 0. It's because our wave function is continuous and smooth. And then our third mathematical constraint is our normalization condition. A good old trusty normalization condition, which anytime we're talking about a wave function is going to come up. So I should expect, as soon as I determine a functional form for this wave function, that if I integrate it over all space, that would be over the range x equals negative infinity to x equals positive infinity, that will sum up to 1. And so let's think about each of these conditions in turn and see if there's if we can solve for these unknown constants. So if psi of 0 is equal to 0, that must mean that 0 is equal to a sine of k times 0, because we're substituting in 0 for x, plus b cosine of k prime times 0. And a little bit of review of your trigonometry course. Remember, sine is equal to 0 at 0, pi, 2 pi, really anything where it's n times pi, where n is an integer. So this first term, naturally goes to 0, and so maybe we haven't really learned anything yet. Cosine is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, and it's equal to 1 at 0, pi, 2 pi, etc. And so this term right here is equal to 1, and that means that 0 is equal to b. In other words, whereas we initially, just based on our guess and check, said, well, it's possible that this wave function could have some cosine character to the function. Now, as soon as we've employed one of our boundary conditions, we learn that in fact, no, this particular wave function only has sign character associated with it. And that is because b, one of the constants, has to be set to 0 in order for our wave function to have this, to be continuous like we expect it to be. Okay, what about our second boundary condition? Now, so we've already kind of figured out b equals 0, so I'm going to toss out this cosine term from now on. Now we know that 0 has to be equal to sine of k times L, because now we're substituting in x equals L into this expression. And remember what I just said about where we expect sine to equal 0? So one way to solve for this could be to just say, oh, well, I can solve for this. If k is equal to 0, then this is equal to 0 as well. That's or a is equal to 0, and that would work as a solution. It's kind of a bummer of a solution because then we just get the trivial mathematical solution, psi is equal to 0 everywhere. And that's mathematically fine, but physically not okay, right? Because that would imply that the particle doesn't exist. And we want to see if there's some solutions where the particle does exist somewhere, so it's actually a particle in a box. So I'm not going to consider the solution a is equal to 0, nor am I going to consider the solution k is equal to 0, because both of those instances lead me to an acceptable mathematical solution that isn't an interesting solution for us. But it's also true that this equation will hold true so long as k times L is equal to n times pi, where n is any integer. So it could be 1, 2, 3, 4, etc. And this is really interesting because now, one, it tells me something about k. It means that k is equal to n pi over L. But what's really interesting about this is I've actually shown that there's not just one wave function that is a solution to Schrodinger's equation. There is, in fact, many different wave functions that are solutions to Schrodinger's equations, and each of them are characterized by this integer n. We'll talk about that a little bit more in just a second. But first, I want us to talk about this normalization condition. So my normalization condition is, now that I've solved for both b and k, it'll be a little bit easier for me to do this integral. I am going to set up the integral from negative infinity to infinity of my function squared dx. And one thing that you'll frequently see in textbooks is people actually just immediately set this integral up from 0 to L because they'll say, we don't need to consider things outside of these two bounds, the particle's not there. I like to be a little bit more mathematically rigorous and remember from up above that our wave function is a piecewise function, right? Where this f of x piece we've now figured out is equal to a sine of n pi x over L. What that means is that I should, just like how you're supposed to do integrals of piecewise functions, probably split this function up into its three distinct pieces. What's happening between negative infinity and 0? What's happening between 0 and L? And what's happening between L and infinity? So I haven't done anything super interesting just yet, other than employing a theorem that's true in mathematics about how if you have an integral over a large range, it's the same thing as splitting that integral up over a sum of ranges that all give us the same overall range. And so between 0 and negative infinity, psi of x is equal to 0. Same thing between L and infinity. And it's only in this middle piece that it is equal to something more interesting. And so now maybe we can see why in our textbook you'll immediately see folks just start solving this middle integral, because this first piece and this third piece all go to 0 because the integral of 0 is equal to 0. Okay, now as for our second piece, which is what we're actually going to integrate over, so we've got the integral from 0 to L of psi squared, which means that we're going to come up with a squared sine squared of n pi x over L dx. And if you're like me, this is not necessarily an integral that you want to do by hand. And the good news for us is that this is absolutely one of those integrals that you can find in Atkins Appendix 1, so that you have the common integral form for it. And I'll just go ahead and write out what you would find in Appendix 1 of Atkins. And what Atkins says, and I'm going to specifically use it exactly as it's written so that we can practice, substituting in our little constants. They would write the integral from 0 to a of sine squared kx is equal to 1/2 a minus 1 over 4k times sine of 2k times a. So applying that to our own situation, now I can see that my overall integral, a is equal to L in this case, little a is equal to L, and k is equal to n pi divided by L. And so this definite integral is going to evaluate to 1/2 L minus 1 over 4 times n pi over L times sine of 2 n pi over L. Oh, and I don't want to forget my a squared. Okay, so for the same reason that it was earlier, this second term is equal to 0, and so that is going to cancel out for us. And that implies for us that this integral is equal to a squared times L over 2. Now, based on our normalization condition, we know that this integral also has to be equal to 1, and that implies that we have a value for a, and that value is the square root of 2 over L. And again, to take a step back, where we were getting this from is our normalization condition, which is a statement that there has to be 100% probability that our particle is somewhere in our box. So we don't necessarily know where yet or where it's most probable for our particle to be, but we do have the normalization condition that it has to be somewhere. And so after all of this work, now we have a solution, or really a set of solutions, that are wave functions that obey the time-independent Schrodinger equation. And they all take the form of square root of 2 over L times sine of n pi over L. And that can be true for any positive integer n. It is typical for scientists to represent the different solutions, what we would call the particular solutions, using a subscript. And so frequently what you'll see in your textbook is someone saying a particular solution psi sub n is equal to, square root of 2 over L times sine of n pi over L times x. And that's just a way of pointing out that there's many different solutions, and so we should index them, and the natural way to index them is by their integer n. Now there's something that we can say that's even a stronger statement about n, and that is bringing this, why do we call quantum mechanics quantum mechanics? Here is why. Because n is restricted to particular values, our range of n is a quantized value rather than continuous. And in fact, to use language that you may be familiar with general chemistry, we call n a quantum number. Excuse me. So what we would say is that the particle on a line has one quantum number, and that quantum number is n. Note that it's not an accident. If you remember from our math, like where did this number n show up? It showed up because of our boundary conditions. And in particular, it showed up because the boundary condition that we told this particle that it couldn't move freely anywhere. It had to be bound or restricted to a certain range. And so it's not an accident, and it's something that we're going to see quite frequently in this course, that boundary conditions, constraints, lead to quantization. And so one of the big chemistry take-home messages that I want us to get, I've shown you this just once for the particle in a box. You're going to have to trust me that this is true more broadly, that confinement leads to quantization. And we're going to see this most famously when we start talking about the hydrogen atom. We're also going to see quantum numbers show up again, and it'll be because we're kind of confining or pulling an electron towards a nucleus in that case. The last thing that I want to point out is that even though our potential between 0 and L is constant, the wave function squared, p of x, is not constant. And so I'm going to show you a kind of interactive GUI of this so that we can see what these probabilities look like for different values of n. But I think it's really important to point out right at the offset that in terms of classical mechanics, I would fully expect that because this potential is the same anywhere in my box, that if I kind of just give this tape some energy and let it float around, that it would spend equal amounts of time in all the different regions of the box. Or in other words, if I took many measurements of this as a classical particle, that it would have an equal probability of being anywhere in the box. That's not true for a quantum particle, and the reason that we know that is that we just solved for the wave function, and it's a sine function. And so let's go ahead and take a look at what those solutions look like. So this will be my little Python plug for the day. I wrote a Jupyter notebook for tonight's lecture that is something that I've posted on our Moodle page. If you're interested in learning a little bit more Python, I encourage you to look over the source code. But for our purposes today, what I'm most interested in having us do is look at the ways in which I've been able to show us some plots of the wave function. And so here's my little function that in Jupyter Notebook you can set interactive sliders. And so this is going to allow us to visualize all the different solutions to the particle on a line using our little interactive GUI. I'm noticing that I forgot to update my y-axis label, so sorry about that. Okay, so starting with our wave function for the n equals 1 value, and you'll notice so I put psi and then a little subscript 1 because we're talking about n equals 1. That is a sine function with 1 on the inside, and you'll notice that this looks like just the top part of a wave of a sine function. Just like we wanted it to, this function is going to 0 at both the points x equals 0 and at the point x equals L. Here on my graph it's x equals 2 because I've set L to 2. But you'll notice if I change this slider and move things around that my wave function is still always bound to be 0 at the points x equals 0 and x equals L. And so what is going to happen as we increase our value of L? How does the shape of this graph change? Well, for n equals 2, notice that now we have one full oscillation of a sine wave. And so some of the notation that will get you used to is saying that this function has 3 nodes. In other words, places where the wave function is equal to 0. Just like in the n equals 1 case, there's always a node at x equals 0 and a node at x equals L, but now we notice an additional node showing up in the center of our box. When we go to n equals 3, we get another node that shows up, so now we kind of have 1.5 periods of a sine function. N equals 4, 2 full periods, n equals 5, now 2.5 full periods. And so hopefully you're starting to see that as n increases, we get more and more wiggles to our wave function. And so we get more and more nodes that go along with that. Similarly, I want you to notice that as we change the size of the box, the wave function always either compresses or expands in order to make sure that there's always, regardless of the length of the box, still the same number of waves present in a particular wave function for a particular value of n. So now that we've talked about the wave function, let's talk a little bit about the wave function squared. And so my wave function squared is, as advertised, literally what I'm asking Python to do right now is take my function that's represented in blue and square that function. And so you'll notice that the shape of it looks similar to the blue curve, but because we've squared the function, its shape changes a little bit, and that's expected. Now, psi squared, this orange curve, tells us about the probability. So if my particle is in the stationary state of psi 1, that means that, unlike classical mechanics, it is most likely for me to see this particle somewhere in the middle of the box. At this point in the course, students often have the misconception of, oh, maybe this means that my particle is kind of actually following the shape of this wave, right? It's traveling suddenly in 2 dimensions, up and down. And I want to disabuse us of that notion, because remember, this is still a 1D particle in a box. Our x-axis is the one-dimensional motion that the particle is capable of, but the y-axis on this graph represents the wave function, not motion in a second dimension. And so the fact that this function is large at, in this case, it looks like the position like x equals 1.5-ish, that just tells me that the particle is very probable to be here. So if I took many measurements of this quantum particle, I would expect to see it in the middle of the box quite frequently. But it does not tell me that this particle is suddenly able to move in 2 dimensions or something along those lines. Interestingly, if we go to n equals 2, suddenly there's no probability in this n equals 2 state that the particle is in the center of the box. Instead, it kind of seems like the particle is either in the left-ish half of the box, or it's highly probable for the particle to be in the right half of the box. And so that tells us we can easily visually see where the most probable positions of the particle are. And it's going to be up to you on a homework assignment to determine for this wave function what is the average position of the particle. I'll show you a couple other versions. So psi of n equals 3, notice, my only thing that I want to notice here is that even though the wave function can be either positive or negative, just like we would expect to be true for a probability, psi squared is strictly positive everywhere. And so again, I'm going to put this Jupyter Notebook up on Moodle, and so that means that you can download this for yourself and interact with it as much as you please in order to help give you a sense of what these different functions look like as we vary n or as we vary L. Okay, so let's go back to our notes and our derivation of the particle in a box. So let's spend the last bit of today's lecture practicing solving for the energy of this particle. So we've solved for the wave function, and I made a claim in last lecture that that means we have all the information we need in order to solve for any property of interest. So let's go ahead and start by solving for the energy of the particle in this case. I'll note that we could, just like we did in lecture 2 for our old example wave function, a different type of wave function, predict the average position of the particle, the average momentum of the particle, or any other physical observable of interest. And it's going to be on a homework assignment that you'll be asked to prove for this particle on a line what is its average position or average momentum for different values of n. But the one that I'll do in our lecture today is the energy. So it turns out for the energy, there's actually 2 different ways to solve. One, just like we did in lecture 2, you can use Ehrenfest's theorem to solve for this. But a second way to solve for this is to substitute our wave function back into the Schrodinger equation. So what I mean by that is we're going to take our time-dependent or our time-independent Schrodinger equation. E psi of x is equal to negative h bar squared over 2m times the second derivative of the wave function with respect to x. And technically it should be a plus v of x times psi of x, but we know that the energy is going to be given by the potential being equal to 0. So we don't need to worry about that second term. And just so you have it here in the notes, remember that our wave function is equal to a sine of n pi over L times x, where a is equal to square root of 2 over L. For the purposes of doing this exercise, I kind of just like to leave it as a because your math will look a tiny bit cleaner. And so what I want you to do now is I ask you to pause the video and try and do this problem on your own. Go ahead and take our wave function, substitute it back into the Schrodinger equation, and see if you can solve for our energy E. So I'm going to ask you to pause the video, take a couple minutes to try and solve this problem on your own, and then when you come back, we'll talk and go through the problem together. Okay, welcome back. So what I am going to do in order to solve for this is I am going to first solve for the second derivative of this equation of our wave function. And so that would be me taking my second derivative of the function a sine of n pi over L times x. So let's go ahead and start with my first derivative. Nothing happens to this constant a. Via the chain rule, remember that's that inside-outside, I first need to pull out a factor of n pi over L, and then the derivative of sine is cosine. So my first derivative looks like a times n pi over L times cosine of n pi over L times x. Now I can go ahead and take my second derivative. Again, nothing happens to this prefactor a, but I need to pull out a second factor of n pi over L, so I'm going to get n pi over L squared in this case. The derivative of cosine is negative sine, and so I need to put a negative sign out here in front, and I get back sine of n pi over L times x. And maybe that's something we should expect because remember, the whole reason we were using sines and cosines in the first place is we knew that the second derivative of our wave function should be equal to the function itself times some multiplicative prefactor constants in front. And so now we can go ahead and set up our equation. So we've got that E times our wave function, which is a sine of n pi over L times x, is equal to negative h bar squared over 2m times negative, so my two negatives are going to cancel out and give me a positive, a of sine of n pi over L times x. So this will simplify quite a bit once we realize that, oops, and I don't let me forget my factor of n pi over L squared. Okay, so this is going to simplify quite a bit because I have a factor of a sine of x on both sides of the equation. So that'll cancel out. And what I'm going to be left with is that the energy is equal to h bar squared over 2m n squared pi squared over L squared. And this will be so important for us that I'm going to go ahead and put this in a nice box for our energy of the wave function. And just like we did for the wave functions, frequently we denote that there are different allowed energy states for this wave function by using a little subscript n in order to indicate that. And so, like we did for the wave function, let's pause and try and think about some of the chemical implications of this energy expression we came up with. The first thing we want to notice is that the energies are quantized. And so my classical particle, there's no reason why it has to have specific allowable values of the kinetic energy that I give it. And saying like, oh, well, it's fine if this classical tape roller moves at 5 meters a second, but 5.5 meters a second, no, it can't move that fast. Classically, we wouldn't expect something like that. But in our quantum world, what may feel very non-intuitively, if you're like me, when I was a student, is that there are specific discrete allowed values of the energy, and aside from that, certain energies are just not allowed for this particle that's living on a line. The other thing that I want us to note is that we already said that the potential energy was 0. So the fact that the total energy is non-zero must mean that this energy expression, E sub n, is entirely kinetic energy that this particle has. Some terminology that we're going to use is that because my lowest energy occurs when n equals 1, that means that E sub 1 is called the ground state of the particle. And anything with E sub where n is greater than 1, those are going to be termed excited states of the particle. And so notice that even the ground state has non-zero energy, but all of the excited states have energy that's larger than the ground state energy. And last but not least, I want you to notice a couple of parameters to this model, if you like. M, the mass of the particle, and L, the length of the box, are two different things that could change about the particle if we either make the box bigger or smaller, or if we substitute in a heavier or a lighter particle. And the energy of these states, E sub n, is inversely proportional to both of those quantities. So for a heavier particle, our energies are going to get smaller, and for a bigger box, our energies are going to get smaller. And we'll talk a little bit more about the implications of that in class over the next couple of days, because even though that seems maybe like a mathematically obvious statement, for a chemist, and especially as someone who wants to make an impact in making different products or different syntheses, or as we're going to study in class, making quantum dot TVs, having these two parameters as something that a chemist might be able to control about a system can lead to some really interesting, really desirable behavior. Okay, so where I want to end us off for today is making a connection between the math that we talked through today, our wave functions and our energy levels, and energy level diagrams like you've seen in your GChem class. So to recap all of the important equations that we talked about for today, we learned that this particle on a line, this particle that's moving in a one-dimensional potential, is characterized by stationary states. Psi sub n is equal to square root of 2 over L times sine of n pi x over L, and has corresponding energies. E sub n is equal to h bar squared n squared times pi squared divided by 2ml squared. And so a wave function is not something that you've seen before. It's certainly not a phrase that we use overly frequently in GChem, but the term orbital is. And so I want to make a statement right now that orbital is a word that's a synonym for a stationary state of the wave function. And so when you start to think about these wave functions for the particle in a box, I want you to start thinking about them as orbitals. And that will mean that when we get to the hydrogen atom, we start talking about the wave functions of the hydrogen atom, that we can make an immediate connection to, oh, I wonder if those are related to the sp, d, and f orbitals that I talked about in GChem. And indeed, that's exactly what's going to be the case. So when we're talking about orbitals, in GChem, you became accustomed to depicting those orbitals on what's called an energy level diagram. So an energy level diagram is something that it's kind of a 1D plot where we're just going to draw the available energies of the system. And by convention, chemists like to draw a single horizontal line to talk about an allowed energy state. So taking our values for the particle in a box, we have a couple of different allowed energy states. And I'm going to try and space these out because notice that our energy is a function of n. And so my different energy levels, which are characterized by the quantum number n, are going to become increasingly spaced out far apart from each other because that spacing is going to increase as n gets bigger. And that's because our energy is proportional to n squared. Now, for these energy level diagrams, if we're dealing with a specific case, which we frequently do in chemistry, where our particle of interest is an electron, we often use arrows to indicate which state that electron is in, or what orbital the electron occupies, if you like that better. And so if my electron is in the ground state, so it's an electron in a one-dimensional potential, and it's in its ground state, how I would depict that on an energy level diagram is to draw my energy levels, just like I did above, but I'm going to use a single arrow in order to indicate that there's one electron that lives in that orbital. Similarly, if we wanted to talk about an excited state, the energy level diagram that I've shown at right depicts an electron in the n equals 3 excited state. And so I bring this up so that as we talk through in class about some of the chemical implications of what a particle on a line might look like for an electron that exists in a potential where it can move about freely in a certain area, that you can make the connection to everything that you did in general chemistry with respect to Bohr's model, the hydrogen atom, trying to talk about what is the energy difference if we take an electron in an excited state and we move it back down to the ground state, because those are the same connections that we're going to start making in class on Tuesday. Okay, so before I get to our summary, let me go back one more time to our set of plots so that I can try and show you, before we end off today, these plots for our values of our different energy level diagram, but using a quantitative Python script so that you can see exactly what these energy levels look like. So here would be our energy level diagram for the particle in a box. I have labeled each of these energy levels with its appropriate subscript. And so if you remember what I mentioned earlier is that our energies are going to get smaller as our box gets bigger. And so let's go ahead and see that happen in practice. So here I'm depicting our box getting bigger and bigger as I move this slider, and you'll notice that that means that our energy levels all go down in energy, and one of the implications of that is that the spacings between energy levels also get smaller and smaller. Conversely, if I make the box smaller, so I decrease L, my energy levels all go up in energy, and one of the implications of that is that the spacing between energy levels also is going to get bigger. The last thing I want to point out is that often you'll see in textbooks people superimpose the wave function over these energy level diagrams. And the advantage of this is that now you can see both the energies and the wave functions at the same time. But I kind of bring this up as a cautionary tale because for me as a student, it was tempting to look at one of these diagrams where you got wave functions superimposed over energies and assume that, for instance, for E sub 5, that must mean somehow that this energy can range between 5 and change and a little over 7. And that's really not the case. This is trying to just superimpose information about the wave function over an energy level diagram. And again, this is all up on Moodle, so you can play around with these energy level diagrams and see for yourself if it helps aid your understanding to have these wave functions superimposed over the diagram, or if you prefer to look at your energy level diagram, just sticking to thinking about the energies. Okay, and so with that, let's go ahead and wrap up for today. And where I want to end us off is with a summary. Today in class we talked about a particle on a line model, and that by definition is a particle who's subject to the potential Vx is equal to 0 inside of our confined area, and it's equal to infinity outside of the area. And that infinity part is to make sure that we guarantee that this particle is not allowed to leave this confined area. We then use the time-independent Schrodinger equation to solve for the wave function itself. And we found out that in fact there are many particular solutions to the wave function for this potential, and they all take the form square root of 2 over L times sine of n pi x over L. N having to be a positive integer, 1, 2, 3, all the way up to very large numbers for n. And similarly, we found out that this wave function has corresponding energies. E sub n is equal to h bar squared times n squared times pi squared over 2m L squared. And last but not least, one of the really important chemistry take-home messages is that even for a potential that's as simple as this, both the wave function and the energies are quantized as a direct result of the particle being confined to a line of finite length. And so with that, let's go ahead and stop for the day, and I'll look forward to seeing you all in class. Have a good day, folks.